And now we are live. Hello, YouTube.
Okay, so I will start and introduce everybody. So welcome to the PhD defense of Thibaut Bessier-Laffosse on model-driven methods for dynamic analysis applied to energy-aware software engineering. And it's my pleasure to introduce the jury members. So we have two reviewers, Anna Cavalli, who is professor in Télécom Sud Paris, Romain Rouvois, professor at the University of Lille. Three other members, Sébastien Moser, professor at University of Quebec in Montreal, Gustavo Pinto, who is associate professor at the Federal University of Pará in Brazil, and the advisors, Gerson Sunier, associate professor in University of Nantes, Massimo Tisi, associate professor at IMT Atlantique, Jérôme Rocheteau, associate professor at ICAM Nantes, and Jean-Marie Motu, associate professor at University of Nantes. And I'm Antoine Beniard, professor at IMT Atlantique in Brest. So Thibaut, you have 45 minutes to present your work. It's up to you.
Okay, thank you for the introduction. Could you please remove the camera during the presentation because, well, my bandwidth is a bit limited. Thank you very much. All right, well, I guess I can start. So this presentation is in the context of energy efficiency. So you may know that energy consumption is becoming a major concern in the domains of software and system engineering for a lot of good reasons. Well, we can talk about ecology, how it is becoming crucial, and limiting the CO2 emission of our IT infrastructures is mandatory. Furthermore, reducing the energy consumption of our smartphones and embedded devices in general greatly improves the quality of service, and long battery lives are a good selling argument nowadays. And finally, well, electricity is expensive, and being able to reduce the consumption can help saving a lot of money. However, if you check this plot on the right, the forecast suggests that the energy consumption of the IT infrastructure is only going to increase in the future. And well, we cannot ask people to stop using their computers. And thus, well, it is important to provide knowledge and tools related to energy efficiency in order to flatten this curve. So now let's talk about energy by itself. You probably know that it can be calculated by multiplying a power with a duration. So if we want to reduce energy, we can either reduce the power or the duration, or both, of course. Energy efficiency has been extensively studied at the hardware, middleware levels, and many approaches have been proposed, such as dynamic voltage, frequency scaling, or even virtualization in the domains of cloud computing. And these are features that are now used everywhere. And we also have some approaches at the software level, such as using the right data structure according to the context, or doing some CPU offloading, or even approximate computing. But the difference is these approaches require the implication of the developer. And there is a common knowledge about energy efficiency, and it is that going faster is enough to reduce energy consumption. It's called race to idle. It works, but it's absolutely not a general rule. And sometimes going faster can increase the energy consumption. So we have a small example here on the right, featuring the Xalan software. And we can see that by adding more threads to the operation, it is going way faster, but the overall consumption only increases. So it shows that, of course, going faster can reduce the consumption, but energy-aware software engineering is complicated. And we have some existing studies that show that most developers have a very limited knowledge about it, and that there is a general lack of tools for helping them designing, refactoring, analyzing, or simply understanding their software. This is especially true in the context of cyber-physical systems. These complex systems are composed of both software artifacts and hardware devices that can communicate, control, or interact between each other, and that can run on very constrained power supplies. These systems are heterogeneous, And they can use many different operating systems, communication protocols, and so on. And this makes energy measurements or estimation very complicated to perform. Hopefully, when these systems are too complex to be analyzed or to work on, well, having a bird's eye view on the system in order to get a big picture can help. We call this big picture a model. So we consider a model as a theoretical description that can help you to understand how the system works. For example, we can consider a big city like London. And well, we can use a model of the city, a 3D model here, to help us. So this model is an abstract representation of London. And we can use it to understand how London is or how London behaves. We could also model the components of our cyber-physical system to help us designing or understand it. So if we consider a small system, we could first design it using a model. So in this situation, the model is a prescriptive model. It is built before. But we could also create a model out of our system. So in this situation, the model is a descriptive model, right? So models are not usually specified freely. They need to conform to what we call a meta model, which describes its syntax and static semantics. So the relationship between the model and its meta model is quite close to the concept of instance in the class-based object-oriented paradigm. So note that models can be executable. They can be either directly interpreted or compiled to executable language. Now, let's see some examples of models. We would like to create a system with some Arduino boards. So Arduino are small boards with a large variety of microprocessors, and they can be embedded everywhere. They can interact with a lot of different modules, and they are great assets to cyber-physical systems. So instead of directly assembling all the pieces of the Arduino together, we could first represent it with a model. So we could use this model on the left, for instance. So this model here is defined with a concrete syntax. So let's see what it means. So at the top of this model, we define the behavior of the Arduino board, and at the bottom, its structural properties. So here, for example, we have a Arduino with 13 pins. On the 13th pin, we put a LED called LED1. On the 10th one, we put a sensor, infrared sensor, IR here. And on top, we define the behavior we want to apply. So here, when our sensor detects something, then we blink the LED, we make the LED blink. So we turn it on, then we wait for 1 second, then we turn off the LED, and we wait for 1 second again. So we can define this model with this concrete syntax, but we can also define it with an abstract syntax here, which is equivalent. So here we say that our model begins with a project element, which is the root. We have a board, which defines the structural properties, and the sketch, which defines the behavioral properties. So here we can see our 2 pins with the LED and the sensor, and the behavior is defined here. We turn on the LED, we wait, we turn off the LED, and we wait again. And these models conform to the Arduino meta model, which defines how we must define Arduino models. So it says that a Arduino model must begin with a project. It contains a board and a sketch. And the board contains pins on which modules are plugged. These modules can be photoresistors, sensors, LEDs, and so on. And our sketch contains instructions, such as instruction to control the modules, or delays, or if statements, and so on. So we could use this model here to generate the code that we want to deploy on the Arduino, or even interpret it in a simulator to verify that it works as expected. But so we were doing a prescriptive model, but we can also create model out of existing artifacts. So this is useful when we want to optimize or analyze an existing system. Let's see an example with a Java program here. So we have a very basic Java program. Here we have just a package which contains a class, which contains a method, MA, in which we have some code that we ignore for the moment. So we can generate a model out of this source code like that. So this model here is defined with an abstract syntax. We have the package on top. Then we have a class CA, which contains a method MA. And both classes and methods have a modifier, public and private. And this model also conforms to a meta model, the Java meta model, which defines how Java models must be defined. So here we need a package with a name that contains classes, that contains a body, which can be an inner class, or here a method. And classes and methods have a modifier with a visibility, right? So now that we know about models, let's talk about model-driven engineering, or MDE for short. So it is a methodology that promotes the usage of models for all the aspects of software and system engineering. So it relies on models instead of the usual code-based practices for a lot of purposes. We can use it to design systems, to generate some code, to refactor the system, to help us understanding it, or even to perform some analysis. And if we remember a bit earlier, we said that there is a global lack of tools and knowledge about energy efficiency. Well, it looks like MDE could be a pretty nice candidate. But when we studied this, we quickly encountered an issue, because the research mostly focuses on models of static information, like the structure or the code. And since energy requires information about the execution, such as duration, a power, well, these are dynamic information. And that is a problem because, well, we need dynamic information to be able to use MDE for energy efficiency. So a common way of performing dynamic analysis is to work using execution traces, which contain information about the execution of the software or the system. But in order to apply model-driven techniques, well, we need these execution traces to be available at the model level. So having a model of cyber-physical system extended with execution traces would be a valuable asset to energy efficiency. However, the models of static information do not naturally come extended with execution traces. We need to be able to inject these traces into the model one way or another for energy efficiency. And because we have a loss of information when working on abstract models, well, tracing the system in the model is complicated. And this is what we studied during this thesis. So we are going to see how we can model traces of a CPS and use them for energy efficiency. Our first part is going to focus on how we can inject traces into the model of static information. Then we will see how we can model traces at the system level. And finally, we're going to see how we could use these traces in model for energy efficiency, and here more specifically for energy estimation. So we can start with this first part, where we will be focusing on tracing in models the execution of the software. So we said that MDE tools are efficient to design and refactor software. So there is a pretty common workflow. We start with an old legacy system. Then we generate a model out of it. This model only contains static information. We use analysis and transformation with model-driven engineering techniques on this model. And then in the end, we do a code generation to generate a new modernized system. So this model here is a static representation of the software, and we said that we need dynamic information to perform energy-related analysis. So the usual way of doing dynamic analysis on software is to insert probes in it. So when the code is executed, the probes are executed along with it, and metrics can be gathered at runtime. So this is how code coverage or energy measurement approaches work. But however, in order to be able to apply model-driven approaches, we need this dynamic information to be modeled. So there is existing work that show that we can that probes can be inserted into executable models, but there is no approach to our knowledge that injects probes in the source code in order to gather execution traces to inject them back into the model then. So this is what we are going to propose here, and let's see that with a small example. So we have a Java code here again. So it contains a class CA with 3 methods, MA, MB, and MC. In our method MA, we have a if condition and a else statement there. So we have 2 branches. In the first one, we call the method MB, and in the second one, we call the method MC, right? So first, we perform a discovery using the Modisco framework, which was historically developed in the NowMod team. So using Modisco, we can produce a static model of this Java source code. So we can see this model on the right here. It contains a package element, which contains the class CA, which then contains our 3 methods, MA, MB, and MC. And here we can see the 4 statements of the MA method. If, the MB method call, else, and the MC method call. So the line attributes in our statement here corresponds to the line in the original compilation unit. So the source code on the left. Now we are going to put probes in our program. So this will enable the tracing of its execution. And we will simulate the execution of this program by passing 0 as a parameter to the MA method. So if we run this method here, instead of directly running the if statement, we will first call the trace here. So using this probe, we are going to locate in our model where is the if statement. So it is in the class CA, method MA, line 3. So we can find it here. And then we're going to attach to this statement a measurement to consider it as executed. Then we continue the execution. We enter in the if statement since we passed 0 as a parameter. And then we trace the second statement here, MB. In the same way, we are going to attach a measurement element to the invocation statement that corresponds to the MB method code here to consider it as executed. And finally, we put a relationship between these statements in order to reproduce the execution trace. Then we have the entire execution trace available in the model by following the measurement relationship this way. So we can then use this model for dynamic analysis as it represents the execution of the software. So this is a first approach we published in a workshop at the staff conference. But we wanted to evaluate how this approach could be reused for other purposes, like doing dynamic analysis. And here we modeled this execution trace with the SMM metamodel, so structured matrix metamodel. So it's a standard and it makes it very easy to reuse for other purposes. And we're going to see that first, we want to see how we could use it for energy efficiency, of course. So there is many approaches for measuring energy consumption at software level, such as Power API or JRAPL. Here we focused on the JRAPL software because it was the easiest to use when we wanted to put probes in our source code. So JRAPL is based on a CPU feature called RAPL, running average power limit, and it is available on most recent CPUs. So performing accurate energy measurement is very complicated on short-running artifacts. So here we only model the energy consumption at the method level. Measuring energy with JRAPL can be done like that. So here is a small example of a Java source code where we put some probes. So at the beginning of the method call, we query RAPL to know how much energy has been spent by the CPU. Then we run the method, we do some computation, and then at the end, we compare how much energy has been spent during this method execution to know how much it consumes, or how much energy the CPU consumed during this method execution. And then we can reuse our SMM model like that to add some additional information about the execution, here energy consumptions. And now we still have our execution trace modeled with SMM, but on top of it, we have some additional energy-related information. And now, well, we can pretty easily reuse it. So here we wanted to evaluate it by showing how models of energy consumption could be used to help the developer understanding their code. So we did not consider in this approach the accuracy of the measurements, but only how we could, what could we do with this model. So we implemented some views using this series framework that can display the execution trace of the software, but with additional information about the energy consumption in it. So here we have the program on the left, and we can see two representations. So this first one here, we can show the trace, so how the execution happened. So we started with a test case, then we run MA, that called MB, that called MC. And then we put some circle of various sizes corresponding to how much energy each method consumed during this execution. So here we can see that the MB method here is the method that consumes the most energy. And here we can see how is distributed the consumption in this method. So this contribution shows that we can easily reuse models of execution traces for purposes thanks to the SMM, to the meta model of SMM. And it is very easy to reuse and integrate in other model-driven frameworks. So we published this approach in a workshop of the SM conference, but wanted to go a bit further in applying it to reduce the cost of regression testing. So regression testing consists in verifying, after some changes in the source code, that no regression have been introduced by running the test cases. So regression testing can be expensive, very long running, and energy hungry. A good approach to reduce this cost is to only run the test cases that are actually impacted by the modification, instead of the entire test suite. And this is called regression test selection, or RTS. So the idea of RTS is the following. We have this test suite here on the left. So we have a test class test CA, which contains 3 test methods. The first 2 test methods checks the 2 branches of our MA method. And the last test here checks the MB method that I do not show because it takes space. So the idea is the following. If we modify our program here, our system under test, let's say that we change the MB method for a MD method called like that. Well, instead of running the entire test suite, we can only run the test cases that are actually impacted by this change. So the test cases that were actually executing this statement here. So here it would be only this statement. And doing so is way faster than running the entire test suite. So we thought that our static model of execution traces could be reused for that purpose. Obviously, RTS has been extensively studied. There is a lot of approaches with a lot of different granularity, but no approaches made usages of models of traces for this purpose. So we saw that as an interesting opportunity to use ours. So we're going to see the approach we applied with a small example again. So here we have our Modisco model on the right that has been extended with execution trace with SMM. So here we introduce a modification in our code source code, sorry. So we change MB for MD. Then what we do is we locate in our model where this statement is and which statement has been modified. So if we check the model, it is this statement corresponding to the 4th line here. And what we're going to do with our approach is simply following the execution trace until we find all the test cases that run this very same statement here. So if we follow the trace, we'll find the if statement here. And if we keep on following the trace, then we will finally find our test case here. So instead of running the entire test suite, we can only run this test case impacted that we saw using our trace model. And it is way faster. So for evaluating this approach, we applied it to some popular GitHub projects, such as JSoup, SRGI, JUnit, or Javelin. So for all these projects, we were able to reduce the test execution time by only running the test cases impacted. So 25% on average, including the build and impact analysis phases. Note that in order to be interesting, we build this model asynchronously. This way, the model can be available when RTS is needed. We perform similarly as other offline, so asynchronous regression test selection approaches like fault tracer, but we are slower than state-of-the-art coarse-grained approaches like ecstasy or hybrid RTS. Although here we argued that by using our model for RTS, It is only one application of this model, and MDE, so model-driven engineering, shines for its reusability, such as energy-efficient refactoring or code coverage, test case prioritization. And relying on standards like the structure matrix meta model makes it easy to reuse and integrate to other analysis tools, such as the platform of the Measure project, which funded this thesis. So this was our first part where we show how we can trace software in models. So we can continue by talking about cyber-physical systems this time and add some interaction with physical devices. So we'll see how we can monitor, model the traces of CPS, and perform dynamic analysis on them. So here again, tracing the execution of CPS has been studied a lot. And a common way is to use, generic monitoring applications. So the usual workflow is first to set up the physical devices to monitor, and then to configure and adapt an existing generic monitoring platform. So it works, but it creates an error-prone dependency because the implementation of the physical part of the CPS is going to drive the implementation of the monitoring of the software part of the CPS. So it requires the hardware to be available first, and it makes the monitoring application complicated to maintain, to develop, or to evolve. Fortunately, MDE is very popular in the CPS design in code generation, and CPS are often modeled before being deployed physically, and several meta models have been proposed for this. Relying on these models to set up the monitoring can help getting rid on this error-prone dependency. A common way of tracing the execution of the cyber-physical system is to rely on a communication protocol such as MQTT. So MQTT conforms to the publish and subscribe paradigm. It is very popular and often used in the CPS domain. So we're going to see how it works. So at the center here, we have a connection broker. And we have some clients that are going to subscribe to a specific topic. And when a given sensor publishes data to this very same topic, all the clients that subscribe to this topic are going to receive the information. At the ECAM, we have emit. So emit is a generic monitor for MQTT clients. It was historically developed and deployed to monitor the energy consumption of Java applications. So emit acts as a MQTT client. So it subscribes to all the MQTT topic it needs to monitor. And then the execution traces produced by the MQTT clients will be received by emit, which can then perform some dynamic analysis on them, some visualization, and so on. And since emit is generic, it can monitor both CPSs, hardware, but also some simple software. So as an example, if we take a Java program like this one on the right, we could eventually put some probes in it to send information to MQTT. And this way, emit will be able to monitor this data. And it can perform some nice visualization, like displaying the power consumption of the software like that. And it's nice. So we are going to base our approach for monitoring CPS on emit, as it was already available and working well. And we propose the following workflow. So we apply it to a subset of a CPS called Sensors and Actuators Network, SAN. So here we have a SAN at the center here that we're going to design using a dedicated meta model. So this meta model, we made it, and it is based on other meta models from the literature, like, SMM again, but also SSN, SensorML, SOSA. So we reused some concepts of these meta models to propose ours. And this meta model defines the structural and behavioral properties of the networks, like which devices are deployed, which measures can be performed on which elements, which data types, which processes, and so on. Then, in order to enable the monitoring of the SAN that we designed with our meta model, we give a SAN model as an input to a model transformation. This transformation produces a set of HTTP queries that can be executed, And when we do that, we can configure EMIT, our monitoring platform, in order to enable the monitoring of the CPS. So EMIT subscribes to all the MQTT clients in the network and can then monitor it, model the execution traces, but also define some analysis and computation to perform on it. So we applied this approach with EMIT and our own metamodel, but the approach by itself is generic and can be applied to any other metamodel and web-based monitoring platform. So here in this approach, we have a metamodel of a system, the SAN model. We inject its entity to a model-driven monitoring platform, EMIT, to enable some dynamic analysis on the system. So we evaluated this approach with a concrete use case in which we model the system with our metamodel and automate its monitoring. So the system featured some thermometer, power meter, a cooling system that would start when the temperature was too high. So we defined a model transformation with the Axeleo software that could generate a set of queries. So here it was in the Postman format, but curl would work too. And we run these queries. So it configured EMIT, which subscribed to the entities in the system. And well, then EMIT was ready to monitor the system, to perform some analysis on them. And finally, we can easily update the model, the CPS, and run again this transformation to update the monitoring platform without breaking it. And this helped getting rid of this dependency we talked about earlier. So this approach was published in the SEAA conference. So this was our second part. Now we move on with the third one. So I've been talking about tracing software and systems, but for this last part, let's see how we could use these execution traces for energy efficiency. So we said earlier that NDE is efficient in the context of CPS. As an example, when a specific program is meant to be deployed on many different platforms, well, using models instead of the usual code-based practices can simplify a lot the amount of work to do. So, for example, the code for multiple different platforms can be generated out of a single model and eventually automatically deployed to all the target platforms, and it is way easier. So when we have models that are executable, running them can produce execution traces. These executable models can be used in simulators before deploying the models to make sure that the model behaves as expected. So there is some work that with additional behavior into executable models, but there is nothing related to energy estimation. And all the approaches, well, the existing approaches in the state of the art can estimate executable language based on trace, but nothing is generic or model driven. So what we wanted to do with this work is to be able to know, based on execution traces, how much energy any model would consume when deployed. So thanks to model-driven engineering, we can perform this directly in a simulator before the deployment or even at runtime once the model is deployed. So knowing this information about energy consumption early in the design process, well, can be very useful to optimize the system while limiting the development cost. So for example, here we have this model here. We can deploy it on multiple platforms. Well, it's interesting to know before deploying it how much it would consume once deployed. So to this extent, we proposed EEL, Energy Estimation Language. So EEL is a small imperative language, or a fish, but we don't care here. And EEL can be used to define models of energy estimation formulas. The EEL model annotates executable metamodel with energy estimation formulas. These formulas only consider one specific set of hardware devices that we call the platform here. And EEL can estimate how much any model of the annotated metamodel would consume once deployed on the known platform. So EEL can perform this energy estimation by studying the execution traces. It can be performed early in a simulator or later on a running system like EMIT. We're going to see how energy estimation formula can be specified. So we have two general manners of defining energy estimation formulas. First, we can simply use the technical specification of the hardware devices. So for example, here we have a blue LED, a King Bright LED, So according to the technical specification, we know that this LED consumes 20 milliamp, so we can specify it in our energy estimation formula. And we know that it will be powered with 5 volts. So we can define this formula. So the voltage of the LED is 5, the current is 20 milliamps, and the power of the LED can be computed by multiplying its voltage by its current, right? So it is pretty simple, but we can then use these values if we had to consume how much energy this LED would consume. Another way of defining energy estimation formula is to rely on measurements. So as an example here on the right, we run an empty Arduino board, we measure its power, and then we average the power we measure to define the power of the board to be 0.123 watts. Okay, so now we are going to see how to use these formulas for doing some energy estimation. So here again, we have a Arduino meta model, the one we saw in the introduction. And we want to estimate how much models conforming to this meta model are going to consume when deployed on a platform with a blue LED. So we are going to annotate this meta model with energy estimation formula. So first, we attach to the LED meta class this formula. We say that the voltage of the LED is 5, the current is this one, so it's a bit lower than the one we saw before because we're going to put some resistor to not burn the LED. And the power of the LED can be computed by multiplying its voltage by the current, right? So we are only going to use one single type of LED in our models, but we could also consider more. Now we are going to attach to the board meta class this variable here, which contains the number of LEDs deployed in the model. So here we count the number of LEDs in the model, so LED.allInstances. Then we are only going to select the LEDs that are plugged to a pin with a high level, level 1 in it, which means that the LED is turned on. And then we count the size of this entity, of this collection, sorry. So this corresponds to the number of LED turned on in the system. We continue. Now we attach to the board the power of LED. So we know how many LEDs are turned on. We know the individual power of the LED. So we can simply multiply both to know how much power is spent by the LEDs of the system. And finally, we attach to the execute operation of our delay this last formula, which multiplies the value of the delay, so a duration, by the power of the LEDs. And doing so, when we will be executing the execute operation of the delay, we will know how much energy is spent by the LEDs during the delay. So let's do a small simulation to see how it works in practice. So here we have, again, our Arduino model. So with the blink part here, we are going to simulate it. So we consider that the sensor detects something. We can enter in this blinking section. So we start by turning on the LED, and then we run this first delay here. So EEL is going to see that there is an energy estimation formula that is associated to the execute operation of the delay. So EEL will evaluate this formula. So we compute it. So it is the voltage of the LED multiplied by the current of the LED multiplied by the number of LEDs turned on. We only have one LED, so 1. And then we multiply that by the duration of the delay, so 1 second. And doing so, we know that this LED here consumed 0.04 joule during this 1 second delay here. We continue the execution, so we turn off the LED. And then we wait again here. And this time we evaluate again the formula, but the LED has been turned off, so the LEDs do not consume any energy during this second delay. So now that we have seen how EEL behaves, we'll see how we can use EEL to improve our models. So we are going to imagine that a developer wants to deploy this blink model here on her platform. But she hesitates between two instructions, either using a if statement, like here, if IR sensor equals 1, or using the wait for statement that is also available in the Arduino language. So the difference is that instead of actively checking the state of the sensor, wait for puts the board to sleep, but adds a considerable overhead when the board wakes up. So instead of deploying the two models and comparing the energy consumption, where she's going to use this model here in the simulator or EEL model, such as this one here that we define in Gmux Studio. and she will be able to know how much energy it consumes. So I'm not going to detail this EEL model because it's big, but keep in mind that it estimates all the Arduino instructions for a specific set of hardware devices. We consider in this model the frequency of the CPU, the number of clock cycles for each Arduino instruction, the duration of the user inputs. We estimate all the possible modules that can be deployed in our platform. So we have infrared sensors, motors, ambient light sensors, a lot of instructions, and so on. So she first estimates her Arduino model with the if statements, and EEL estimates it to be 160 joules, right? Now she replaces in her simulator the if with a wait for, and then she simulates the same scenario, but still with the same EEL model, and this time it consumes 1.02 joule. And now the developer knows which model she should deploy to be more energy efficient. So this energy estimation approach was published first in a workshop at the Models Conference, and then later to the SLE conference. So we wanted to evaluate two things here with EEL. First is its expressiveness, and then its accuracy. So for the expressiveness, we modeled some instruction-based energy estimation approach we found in the literature. And then for the accuracy, well, we modeled a Arduino program, and we estimated it with two different platforms that use different devices. So here on the right, the blue plot corresponds to the power we measured during the execution scenario using one of the two platforms. So we had some motors at the beginning, and then some blink there that we had to estimate. So with two platforms, we were quite accurate. So it showed that when the executable language is expressive enough, well, we can calculate some accurate energy estimation with EEL. Furthermore, here again, we modeled our energy estimations with SMM. So we were able to define some views using, again, model-driven tools, which can help developer locating some energy-consuming methods or classes in their models. So here, for example, we have an execution trace here on top here, which is linked to the model we're executing, and the color indicates where is located the energy-consuming method. So now I guess it's time to conclude this presentation. So we studied the lack of dynamic analysis options in MDE, and we proposed several contributions that can be applied to energy-aware engineering. So we first present an approach to model the execution traces of software. So we applied the approach to Java, but the approach by itself is language agnostic and could be applied to other languages. So we show that this model that contains Z traces can serve several purposes, including energy efficiency. Then we proposed an automated approach to enable the monitoring of cyber-physical systems. The generic platform we use, Emmet, relies on execution traces to perform some dynamic analysis on a running CPS, but also on simple software. And finally, our last contribution is a generic approach that relies on execution traces to estimate the energy consumption of softwares and systems. So we modeled some dynamic information along with some static models, and we were able to reuse it for several purposes: energy consumption understanding, regression test selection, and finally, energy estimation. So to sum this in one sentence, we can say that the static models in which we injected dynamic information were a pretty valuable asset to energy-aware engineering and are very much worth studying for this purpose. Now, this thesis opens a lot of interesting perspectives. So first, considering the Modisco models with the dynamic information we put in it, well, we could do many more interesting analyses, such as code coverage, linking it with requirement models, performing RTS with variable granularities to do some fault localization, and so on. We could also do some more interesting stuff with EEL and energy-oriented refactoring in general. For example, if we consider a EEL model of one language, we could define a set of different refactoring to do, defined as model transformations. And by applying this transformation in the code, we could compare the energy consumption the refactoring, and identify eventually some anti-patterns of energy consumption, or even good patterns of energy consumption. Also, estimating some GPLs with yield could be interesting too, by decorating some Java bytecode, for example, or some intermediate representation of LLVM and other GPLs. And we could compare the estimation across the languages. I think it would be fun. And finally, well, automating the definition of the yield model could be very interesting. We could gather some information dynamically and applying some machine learning on the data to automatically generate some energy estimation formula for yield. And it would ease the definition of the yield models because, well, defining it by hand is long and tedious. So these are the references I used during this presentation. This is our scientific contribution, some publications. So 1 journal, 2 international conferences, and 3 workshops. And finally, this is the last slide. So thank you very much for your attention. That's Anil. So I guess we can start the question now.
Okay, thank you, Thibaut, for this presentation that meets the time script exactly. Thank you very much. So now